information about the ideal spring that I was investigating. So first of all, titles. Force in newtons versus distortion magnitude. Oops. Magnitude in meters for an extension spring. And you could be more descriptive than that, but that's my basic baseline descriptive title. Make sure that you have a numbered table or figure when you're doing these things. A reasonable header, formal header, might be force provided by spring. You want to make sure that you have that variable in there, comma, Fs, have the unit in there, newtons. Spring distortion magnitude. And you may find that the things that I'm including in these headers exceed what some teachers ask of you. Maybe I fall short of some other ones, not many. But make sure you just follow the house rules, whatever the course is. Okay. And let's just say that I did this experiment. I let a mass hang from a spring, and I let that mass just sit there at a constant height. That would mean that the spring force would be equal to the force due to gravity pulling down on the mass. In other words, I had a spring hanging from, I don't know, a retort rod or the ceiling or something, and the mass was hanging off of that spring such that Fs was equal to Fg because it was just hanging at a constant height. The data looked like this: 5.00 newtons, 10.00 newtons, 15.00 newtons, and 20.00 newtons. Those are my forces in my pretend experiment. 0.20 meters, 0.04 meters, 0.060 meters, and 0.080 meters. Notice that whatever my instrument was, I must have been using a measurement instrument. I would have had the same number of decimal places for each of these values. If I was calculating that Fs value and I was using something like 9.81 meters per second squared to calculate the Fg value, then that would mean that all the values in this column would have 3 significant figures, not necessarily uniform decimal places. And so that's something that I want to draw attention to. Where did the data come from? Was it something that I measured with a tool or calculated? And if you calculated it, you have to have a sample calculation for where the values came from. When I look at this, my grade 9 math skills tell me that there's a common first difference. Or maybe it's grade 10 math skills, depending on your teacher, I suppose. But that means that it's linear. And what we could say in terms of a proportionality statement is that the spring force is proportional to delta x. That means linearly proportional to. We take this data and we say we're going to produce a graph, and I want to make sure that as I do this graph, whatever we do, don't force lines of best fit through the origin. It may be that lines of best fit do go through the origin just by chance, but my goodness, if I have one more teacher from another science area telling me that physics has said that you have to force things through the origin, I might just lose my mind. I have never said that. Never have things go through the origin, okay? Unless they really do. Like you just don't force it through the origin artificially. Now, I'm going to turn the page because I want to have my axes set up nicely, and I'd like to talk about spring force, Fs in newtons. You can pause it there if you're on video, but I'm going to rotate it back. And then on the horizontal axis, and obviously if you can format this in software when you're making a lab report, hey, that's great. Distortion magnitude. In meters. Oh, shoot, I forgot to shoehorn in. I have whiteout. Delta x in meters. And if I actually go through and I plot the data that I have in my data table, I'm going to have a scaling here. It looks like, just based on how my axes are set up, oh, what did I say here? 1, 2, 3, 4. Yeah. 1, 2, 3, 4. I did a little bit of forward thinking on this one. And I said that every 4 squares was going to be 0.01. So 2, 3, 4. 0.02. 2, 3, 4. 1, 2, 3, 4. 0.04. 2, 3, 4. 1, 2, 3, 4. 0.06. 1, 2, 3, 4. And make it in 1, 2, 3, 4. Oh my gosh. I'm not really happy about where that ended based on where the arrow is, but I did manage to squeeze in 0.08 just to the tip of the arrow, and there's going to be some people that say, well, you really should extend the arrow just a little bit. Okay. So in the vertical axis, again, I went back and I scaled this, and I think I did every 4 squares. 1, 2, 3. Oh no, I didn't. Oh, this is going to feel just a little bit dirty. 1, 2, 3 squares. 1, 2, 3 squares. 1, 2, 3. 1, 2, 3. And we're going to go up by 5 for every 5 squares. What a terrible scaling. 5.0. 10.00. 15.00 and 20.00. Obviously, if we're using software, this is going to be better. But then when you go to plot my data, based on this scaling and the fact that I definitely cooked my numbers to have easy to deal with numbers, get my line of best fit out of my actual data. Your data would never lie on the line exactly like this. Your data would be something slightly less than ideal because the world is a wild, wild place. They even call it the WWW, Wild Wild Web, right? I'm sure that's what it stands for. All right, so when we do the line of best fit, it looks like that. And your real data would have some data below, some data above. Line of best fit, if you're using some software like Desmos or something like that, then obviously it's going to create that line of best fit for you. But what we would look at whenever we have a line of best fit like this is the rise over run. Oh, you know, we should really throw in a title before we talk about rise over run. And you know, I have a table that has a title. It seems like the figure could have a very similar title. Force in newtons versus distortion magnitude. In meters for an extension spring. Oh man, line wrap. Okay, ourselves a little underline. But yeah, we could talk about the slope of this, and of course the slope, rise over run. And we don't really necessarily write the words rise over run. I'm just speaking younger grade language here. Delta Fs over delta, and this is weird, it's delta of delta x. Oh man, what a weird notation. The change in length. Double delta. That's odd. Doesn't happen very often. Anyway, make sure that the 2 points that you choose for this slope calculation, and they don't have to be actual data points, they just have to be points on the line. So I'm just gonna like pretend that I chose 2 random points on this line that actually are on the line, but make sure that they're as far apart from each other as you can make them, because the further apart they are from one another for your rise over run calculation, the less you're going to introduce percent errors if you're doing any kind of human approximation, right? So make the rate triangle as big as possible. Make sure that the 2 points are as far from each other as possible. when defining a rate triangle. But actually on the line. And the only reason I really say that but is that if you have a line of best fit where there actually were some outliers that were kind of off the line, but your line of best fit still sort of fits the data, don't choose one of the outlier or one of the things that data points that aren't exactly on the line. These data points actually have to be on the line, right? That's not really truly an outlier. Something out here would be an outlier. That would be weird. We'd have to address it. So I got this y equals mx plus b equation, and any line of best fit could be thought of like a y equals mx plus b, a line equation. Only in this case, look, this one happens to go through the origin, so the b just drops out because there's no y-intercept. Instead of y, we would use fs in its place. We're going to have a slope, so I'll just leave that as a blank. And instead of x, I mean, this is kind of convenient. We actually use delta x because that's the variable we have for the distortion magnitude. And when I'm going to calculate the slope, remember, we're using that delta fs over delta of delta x. I'm just putting brackets around it to separate the two deltas. And the name that we give, or sorry, the variable that we give to that slope is k. And we can say where, quote unquote, k is the elastic coefficient of the spring. There are going to be some other people that call it the spring constant. I mean, it's not a universal constant. It would just be a constant for that particular spring, that particular ideal spring. So every ideal spring has its own characteristic k value, okay? Because it has its own stretchiness. Because that's really what k is. I mean, when you look at the units for k, K has units of newtons per meter. We're talking about how many newtons it takes to distort a spring by how many meters. That's really like a quantitative way of talking about stretchiness. That's all. So it has its own characteristic stretchiness. It has its own characteristic K value. And so when we're talking about things having a characteristic K value, really we're coming down to this force calculation where we say Fs is equal to K times delta X, and then so frequently in textbooks, people will put a negative sign in front of it. Now, that negative sign isn't really there mathematically. It didn't come in from a negative slope. The reason that it's there is, and I'll just like put this in as a little arrow, I'll just say not truly associated with slope. How do you spell associated? CIA? Yeah? More of a reminder. And it's really there as a reminder to remind us that whatever we do to a spring, it's going to work against us. It's a negative sign. And people say, well, how come they didn't do that with the friction formula? How come the textbooks don't put a negative sign randomly in front of every friction formula? I don't know. But that's why that negative sign is there, because springs always work against us, okay? And we call this Hooke's law for ideal springs. Hooke's law for ideal springs. And you'll see words like spring constant. And you'll see words like spring coefficient. And if you see some other words other than that, let me know, and I'll let you know that it's probably just a synonym for the same thing, okay? Now I've got this graph that I want to fill in some values for. I don't want to put any numbers on it. I just want to talk about the shape of the graph. But I want to add in a title first. Spring force versus distortion. Spring force versus distortion for 3 springs. And This is a what if kind of. What if I did an experiment, kind of like what we have described up above, and I was to figure out or produce the graph. Oh, you know what I never did back up here? Was actually calculate the K value for this. Is everybody okay with just saying, yes, we could actually do this? Yeah. I'm going to move on then, okay? We can divide. Fair enough. All right, so back down to this. If I had a graph like this, and I'm just going to say, in a what if scenario, I got spring A that produces a graph like this. I've got spring B that produces a graph like this. I don't know if you can tell if this is green or not. You know what? I'm going to use pink just so that you can really tell. I got spring C that produces a graph like this. Okay? So 3 different springs, 3 different slopes. And if somebody were to come along and ask the question, here's question A. Oh, question A. Which spring is the most stiff? You know, that's a language that people often use. How stiff is the spring? Which spring is the most stiff? Anybody willing to tell me which of these strings, A, B, C, is the most stiff? Yeah.
A, because it has the greatest slope.
Say it again.
A?
It has the greatest slope?
Yeah.
Yeah, but it does have the greatest slope. Does that mean it's the most stiff or the most stretchy, though? We gotta have a rationale for this.
The most stiff.
Why do you think it's the most stiff?
Because it has like a bigger coefficient.
Because the coefficient's bigger. So it is the steepest. It does have the biggest K value. But like, why physically? Why does that mean that it must be the most stiff? Araf? Yeah, look at this. You see that A requires a lot of force. We don't have a numerical scale on the vertical, but see how A requires a lot of force to get the same amount of stretch as C? Look, delta X is how much you stretched it by, right? All 3 of those got stretched the same amount by the end. So if I'm thinking physically about this, they all got stretched the same amount, but A took the most force to do so. We want to know why. We don't want to just say because it's bigger, although you're right, you were right. But I want to know physically, like, why, right? So we're going to say A, and then if we were to throw in a part B and say explain, the explain would be it takes more force to cause the same stretch. We always got to be able to put physics in context and understand how it works in the real world, right? And sometimes that means being able to explain it, not just to other people, but to ourselves.